Festival like this is a beautiful indication of the kind of thing that I truly, truly believe in, and I think makes our society more whole and more pure.
We do not take it for granted that Boulder was chosen as the first North American satellite festival. It's a huge honor we will not forget, and we are enriched because of it. We are indebted to both the local and international people that came together to make that happen, and we hope it's a tradition that continues for decades to come.
Literary festivals like this one build up an environment and an ecosystem to nurture readers and to promote the business of books. They provide an invaluable forum for writers to connect with other creative people.
We sit there peering into those electronic grids in front of our eyes, and it only increases the desire to see the real thing in the flesh. To actually hear an author speak firsthand, to read from their work, to hear the tones of their voice modulate as they read their most treasured passages of prose.
For us, it's special. This was our mothership, and it continues to be. The other editions that we have across the United States are smaller versions, different programming, but smaller versions.
Welcome back to the last session of the day today. On behalf of JLF Colorado Festival co-directors Namita Gokhale and William Dalrymple, Teamwork Arts, Boulder Public Library, and the City of Boulder, we welcome you to this session. A profoundly important imperfection, understanding our universe. Eric Cornell in conversation with Priyamvada Natarajan. The notion of imperfection usually carries negative implications and the idea of defect. But what is the significance and implication of the concept of imperfections in the field of physics? How did it impact our universe? Eric Cornell, professor of experimental physics from the University of Colorado and Nobel Laureate for Physics in 2001, speaks with distinguished astrophysicist Priyamvada Natarajan, evaluates the one moment in time 14 billion years ago that made it possible for us to be here today. Eric Cornell has received his PhD from MIT in 1990. He is a fellow of JLF University of Colorado and a senior scientist with NIST. In 2001, he, along with two other scientists, won the Nobel Prize in Physics for discovering a new form of matter, Bose-Einstein condensate. Priyamvada Natarajan is an astrophysicist and professor at Yale, where she's also the director of the Frank Program in Science and the Humanities. A recipient of many awards and honors in recognition of her seminal contributions to the study of dark matter, dark energy, and black holes, she's also the author of the critically acclaimed book, Mapping the Heavens, the radical scientific ideas that reveal the cosmos. We are delighted to have Launchora as the podcast for this session. They're the podcast partners for this session. This conversation will be followed by a Q&A, so please feel free to send in your questions. All our sessions will be available to view on our Facebook page, JLF Lit Fest, and on our YouTube channel, Jaipur Lit Fest JLF. Do please follow our handles on Facebook, Twitter, and Instagram, and be notified of upcoming sessions. Also, stay tuned to the jlflitfest.org /Colorado for the full schedule and information about our speakers. In these unusually difficult times, it has been difficult for us to bring the festival to you without charging a registration fee. We encourage you to generously donate towards the cause. Please do help us to ensure a free, seamless, and continuous flow of knowledge. Do donate generously. Ladies and gentlemen, a profoundly important imperfection, understanding our universe. Eric Cornell in conversation with Priyamvada Natarajan. Over to you, Priyamvada.
Thank you so much for that very kind introduction. I'm really excited to be here. I wish this were in person in Boulder, and we were sitting across from each other in one of those lovely rooms in that beautiful city. But hey, we are all healthy at this point, so I guess we have much to be thankful for. And I'm really grateful for all of you who have tuned in to listen to us. So Eric, it's really exciting to talk to you. And I think I was surprised at how many ways our paths have crossed. I last saw you when I was a JLF fellow almost a decade ago now in Boulder. So I wanted to just start off by asking you a little bit about the sort of incredibly revolutionary work that you did. We might as well get the Nobel Prize kind of out of the way, because I know that you're doing a lot of interesting work well after that and right now, which I want to get to. But I was just curious about what it felt like, those moments in the lab, and when you knew that you had sort of chanced upon something that nobody else had figured out or seen before. What did that feel like?
Well, Priya, first let me say that I'm thrilled to be here talking with you. It's true. I looked back. We've crossed paths in many different ways. That same year, you were here at Boulder for a while. We haven't crossed paths exactly, but our paths have intersected. I was a visiting fellow at Trinity College, where you were also a fellow at Cambridge University. And that same year when you were doing your sabbatical here, I later did a sabbatical in the south of India, where you originally hail from. So I feel like we have a lot of common.
You know, I was an undergraduate when you were a graduate student. So
Good point. I think this as well.
Yeah, so it's interesting. But so, yeah, I would like to hear you talk a little bit about the what it felt like to kind of create this thing in the lab, you know, the first time condensate.
It was an exciting time. In those days, I was working very closely with another professor, Carl Wyman, but also with 2 young graduate students and a young postdoc who were working. And it's, of course, one of the hidden secrets of experimental physics that the professors get all the credit. But so much of the work and creativity and energy come from the young people, the trainees in the lab. And I was sort of poking my head into the lab on a first a daily and then an hourly basis as we got closer and closer, meddling around. A very interesting thing happened. In addition to the university, I work for the federal government, the National Institute of Standards and Technology. And one of the things of being associated with a government is there's constantly reviews and panels and what have you. And the NIST sent a panel of distinguished visitors to come to JILA, where I am in Boulder, to review us. And the standard drill when you're being reviewed like this is you clean up your laboratory, you cease all activity, and you focus on the visiting committee. Mm-hmm. The visiting committee knocked on my door and I let them in, and the lights were off. The lab was a mess because we were working. And basically, I barely didn't give them the time of day because there was no way I was stopping for the committee, no matter how distinguished they are. And later, it was only a few weeks later that the word went around the country that we had seen this thing, Bose-Einstein condensation. And I'd heard from a couple of them saying, like, we suspected something was up. You could not possibly have been so discourteous to us without something going on. It was an exciting time, and unusually for scientific discoveries, it was pretty clear almost right away. There was getting very close to a eureka moment. So often these things, clarity develops over the course of years or decades. In this case, in a matter of hours, we thought, yes, we've got this, and we published only a few weeks after that. Very exciting times. The world's lowest temperature at the time.
Say,
So
yeah.
close, yeah. So close to absolute zero.
Yeah, and so many firsts in one go, right? Sort of many firsts
Yeah.
kind of coiled together. And of course, there's this India connection with Bose-Einstein condensates.
Satyendra Nath Bose, the distinguished Indian physicist who was working in those days at the University of Dhaka, then part of India, and had this brilliant idea having to do, he had an entirely different way of understanding the color of light that comes off from a hot body, black body radiation. He was able to describe this spectrum with no reference at all to electromagnetics, just using a statistical reasoning. He couldn't get it published, which is often the case with new ideas.
Right. He wrote to Einstein to get him to support his paper getting published.
He sent it to Einstein, pointed out to Einstein that Bose, had translated Einstein's work into English for publication in India. And Einstein basically returned the favor, said this is a great paper. He translated it to German, then the language of, mostly the international language of physics, and arranged for it to be published in Germany. And more than that, Einstein was so intrigued by the ideas that he worked on the same ideas too, which is why now it became known as Bose-Einstein condensation, predicted by these two men, 1924 and 1925, but not seen until 70 years later in Boulder.
And I think what was intriguing about that particular time in India is, India, of course, was under colonial rule at the time. So you had Satyendranath Bose, who gets supported by Einstein, gets published. And you had Chandra a few years later studying at the University of Madras as an undergraduate. And he has this paper, once again, combining sort of quantum mechanics and classical physics. And he gets Willie Fowler to help him get that paper published. This is such a different era, right? So now we just write a paper, we post it on AstroPH, and we send it to the journal. Yes. And it's hard to imagine what that must have been like, what an arduous task it is, even after coming up with something really original, to actually get it published, and the endorsement that you needed from someone great. But the fact that these guys off, right? I mean, I think, this is one thing that I've always been intrigued by, that, during colonial rule in India, you had, these sort of brilliant minds that were recognized. And I wondered if some of it was just because, the desire to show that science really knows no boundaries, and science is really, to be nurtured wherever it blossoms. So because, you had Chandra, you had Raman, you had Satyendranath Bose, you had many of these minds. Yeah. And Raman, exceptional, right? Because his discovery and getting the Nobel Prize, it was like within 2 years he got the prize, right? I mean, the Bose-Einstein condensate, of course, took 70 years to actually generate in the lab, but his. Yeah. But I wanted to then move on to the theme of today's conversation, which of course is of great interest to someone like me who's a cosmologist, because of this fundamental lack of symmetry between matter and antimatter in the very, very early universe. And I know that you have gotten very interested about this question. The fact that, very early on in the universe, you expect just the right amount of matter and antimatter, identical amount of matter and antimatter to have been originally produced. But in the very early universe, in the hot, dense state, you can have matter and antimatter sort of come together, annihilate, go poof, and just become energy. But eventually, for some reason, our universe seems to have had an excess of matter over antimatter. It's almost like there was a loaded dice, right? And that there was slight more matter than antimatter. And I know that these are questions you are starting to look in experimentally now, right?
You know, maybe there's a little bit of a theme in my work, which is I'm interested often in things which aren't quite perfect. You know, Bose-Einstein condensation was so very, very close to absolute zero. Absolute zero is sort of an Olympian ideal of perfection and cessation of movement, perfect order, no entropy. And yet scientifically, most of the exciting things happen on your way to absolute zero. Absolute zero is like heaven, a good place to be, but not necessarily interesting for a scientist. And as you point out, so many things are symmetric, and we so often associate symmetry with beauty, and we look for it in physics, and it's so often there in physics. One of the early symmetries was that there were almost exactly the same number of protons as antiprotons, electrons as anti-electrons in this gas, and then they all found each other, annihilated. Had this perfect reflection symmetry between matter and antimatter been truly perfect, we'd be in a very boring universe. All the matter would have found the antimatter, nothing left.
Right, and we wouldn't, right? We would not be in the first place, yeah.
Everything we care about that we find interesting, you know, humans, stars, God, love, science, anything you care about arises from the fact that it wasn't perfect. This little beauty mark on the face of this perfect symmetry that gave rise to the interesting thing. And so that's always been fascinating to me. It's probably a coincidence, but
right.
my interest in like studying and understanding this profoundly important imperfection happened to happen around the same time that I became a very asymmetric person. This was about 16 years ago.
Ask you about that.
I'll just stand up a little bit. I don't. Yeah. You can see I don't look quite as symmetric as most people.
Yeah, I was going to ask you about that very traumatic experience that you went through, and were you aware of what was going on when your arm was actually amputated, or was this a shock that came out, or?
No, I was feeling poorly. My arm hurt. I went to the emergency room. They couldn't understand what was wrong with me, but saw that my blood pressure was going down as I was indeed going into septic shock, and I fell into a coma. Almost died, and was unconscious for several weeks. During which time it was. During this time. It was, I think my family was quite concerned, obviously. The fear was that I would die, but in fact, I didn't. And by the time I woke up, I was essentially out of danger. It was a little bit of a shock to wake up and find myself missing an arm. So.
And it was a bacterial infection, right? That they had, it was a rare bacterial infection that you had contracted.
Yeah. Necrotizing fasciitis, sometimes called the flesh-eating bacteria, which starts off oftentimes just as a ache or a pain, and then gets much worse. And by the time they figure it out, oftentimes it's too late. But in this respect, I was lucky.
Gosh, I'm glad that with this minor asymmetry that you're still well and here, and yeah, that must not have been an easy time. You know,
it was. Yeah, go ahead.
No, go ahead.
I was going to say, I believe it was terrifying for my family, but as I say, I was blissfully unconscious. So it was a shock when I woke up, and everyone said, "Eric, you're so very lucky. You've survived this near brush with death." And I'll admit that first day I didn't feel so very lucky. I came around to thinking about that when I came better to understand how touch and go it really was. These days, if you're going to lose one limb, I strongly recommend you lose your non-dominant arm. That's the one you can most readily give up, and not that big a deal.
Right. Yeah. Going back to the imperfections of the universe, I was curious whether you had a pet speculation about what might have caused this matter-antimatter asymmetry. You know, I have one that I kind of like, and it's a bit indulgent. It's just to say that perhaps we happen to live in you can imagine where I'm going, right? As a cosmologist, maybe we live in the portion of a portion of the universe where you have this asymmetry, and that, there are infinitely many other patches in the universe in which this may not be the case. And I mean, there may be a patch where the converse is true. A patch which is dominated by antimatter rather than matter. So what is your favorite explanation? It's of course all speculative, right? We should clarify to everyone who's listening that we're just riffing at this point. We don't actually know the origin.
We're completely riffing, and part of the point of the experiments I'm working on is to try and bring some sort of data to the problem beyond the mere fact of our existence, which is indisputable, and as you point out, inextricably linked with this strange imperfection. Maybe, as you say, it's no coincidence. Of course it has to be, or it'd be this way, or we wouldn't be there. And if you're willing to say the universe is so large that it sustains many different varieties of physics, then it seems like not such a coincidence, but who knows? If you want to learn about this event, traditionally there are really three ways of going back and learning about these ancient days. The first one, Priya, I'm embarrassed, you know much more about than I do, but this whole idea of the telescope as a time machine.
Right, looking back in time, right? So I should just kind of clarify that whenever you are looking out into the night sky, you're actually peering back in time. So to just get a feel of it, for example, right, that the sun is our nearest star and it takes 8 minutes for light to actually reach us. So when we see the sun during the day, you're looking up, you're actually seeing the sun as it was 8 minutes ago. You're not seeing it at the moment that you're actually witnessing. So imagine all the other structure we see in the universe is much, much further away. So it takes light longer and longer time. And in fact, many of the galaxies that we can now see with the Hubble Space Telescope, the light almost left those galaxies about 12 billion years ago. So we don't know what those galaxies look like today. We just see a snapshot of what they looked like before. So you're absolutely right that, telescopes and these instruments of looking out into the night sky are really sort of time machines that are allowing us to see the early universe. But alas, we can't go too far, right? So we can kind of indirectly map almost out to about 400,000 years after the Big Bang. So we actually get signals from there, but not beyond. So there's sort of a limit.
Yeah, it's there's a curtain drawn over us. We see the black gauzy curtain, and then beyond that we can't see. Another tool, say the second leg of a three-legged stool. There's the telescopes. They're the accelerators. These colliders where they smash a proton and antiproton together, or two protons together, they smash together at enormously high energies, and they're trying to reproduce the conditions of the universe. At the moment the protons crash together, it's phenomenally hot, temperature is comparable and to these early universe temperatures. And the thought was, when they built the LHC, the very largest current collider in Switzerland and France, that would yield hints about this. But it's been, to many people, a bit of a disappointment, that machine, in the sense that it did not actually display some of these exotic particles that people thought were responsible. You asked what my favorite explanation is. I don't have a favorite explanation, but for many years people invoked this concept of supersymmetry as a way which solved a lot of problems, including versions of supersymmetry. This original it came as an explanation for this original all-important imperfection at the beginning of the universe, but that was not borne out in the LHC. That was not seen there. So one day maybe they'll build a bigger accelerator, but that day is probably 30 years off. So there's a third way, and that's my way, which is making very, very careful measurements. I don't have to explain to you, but different imperfections in the universe we strongly believe they have to be balanced out. If there's so much imperfection in asymmetry in charge, and there's got to be some asymmetry in time or some in mirror reflection. These things balance out together. And therefore, we really believe that we should be able to see fossils. So we can't go back and look at the dinosaurs, but we can see dinosaur bones. We can't go back and look at the Big Bang, but we can see fossils of those early imperfections. If we look at modern particles.
Right? I mean, this is what is so cool. This is in the laboratory today. You can recreate some of these fossils, right? Yeah.
Yeah, that's the hope. And so you really are a cosmologist. You really are an astrophysicist. I pretend what I really am, my day job, you might say, is a precision molecular spectroscopist. I take modern day molecules in the lab and look for tiny deviations from symmetry. You know, these tiny molecules should be very symmetric, but if they're not, that's a hint. And the thing that we're most interested in is an asymmetry in maybe the most common, most garden variety, best known particle, which is the electron, the thing that carries charge in wires. It's just everywhere. Everything is made up of electrons. And as far as we know, they're a North Pole and a South Pole. They're like little bar magnets. But it could be that in addition to the North Pole, the South Pole, they could be slightly different. We know that they're negatively charged, but maybe the North Pole could have a little extra electric charge and the South Pole a little less. Right. After all, the Earth, here on Earth, the North Pole and the South Pole could hardly be more different. One's sea ice and one is mountains and so on. One has polar bears and one has penguins. If you ever see polar bears and penguins together, you know you're in a zoo. But electrons are incomparably more symmetric than the Earth is. You know, they already we can tell that. But the theoretical physicists I take my cue from assure me that if you look carefully enough, these particles ought to have these residual asymmetries. In some sense, asymmetries left over, or at least echoes of these original imperfections.
But these are very, very difficult and high precision measurements, right? So very challenging.
Very challenging. I've been working on it for, I'm embarrassed to say that, I've been working on this for 16 years. And we've made a lot of progress. We, meaning my colleague, Professor Jun Yi, and I, and all of our students and postdocs and so on. But we haven't yet been able to find it. We've learned a lot of things. We've developed brand new techniques in molecular spectroscopy to make it work. And one more connection, one of the techniques we use is known as stimulated Raman transitions. And once again, there's the Indian connection for you. Raman and Bose were, I don't know if they were students together, but they were within a year or two of each other at University of Calcutta, if I'm not mistaken. So, yeah, so.
And of course, you have spent time in Bangalore, right? Not at the Raman Research Institute per se, but you've spent quite a bit of time, like a few months in Bangalore.
I did. It was a wonderful time in my life. I brought my family. My children went to school at a school there in Bangalore. My wife played bridge with Bangaloreans, and I went in to work on, in principle, I was studying new techniques of green energy, ways of generating energy without creating as much carbon dioxide. I did not make a lot of progress. That said, I have no regrets. They were wonderful 3 months there in Bangalore.
This sounds wonderful. So Eric, I mean, I guess it's partly the Nobel allows you to kind of try out a lot of different things, take some intellectual risks. I'm sure it helps, doesn't it? It sounds like you have a lot of interest, right? Regardless, in the first place.
I had an interest in the first place, and it's true that I can take some risks. You know, if I spend a few months studying green energy and I have no results, I'm not going to get fired. So it gives me a little bit of freedom, the Nobel and the previous success.
Yeah, but I mean, I think what is very heartening for me is your choice of problems. The fact that you seem to want to use physics for some good, to see if there's something we can do to solve these big global problems. And this, you have this desire to not just be focused on yourself and your experiments that you and your group can do and serve the physics community for us to learn sort of, in this corner, but challenging problems that could impact the wider world and that are really, really urgent. And I think, what I find, coming back to the fact that someone like you took months off to work on this, is it disheartening for you as it is for me that we live in a country where there's so much denialism of science and climate change, and especially right now with the pandemic, the sort of science is really under siege? Are you as down about it?
Yeah. I despair that in our highly politicized atmosphere right now, everything, you make a simple statement of declarative fact, and one party will seize this and take it as their banner, and the other will say this is the devil incarnate. Facts don't really have a political point of view, and so this is it's quite depressing to me, both in terms of as you say, this time right now and the time of the pandemic, if ever, where there are time for us to learn the lessons of science, to let this people with some knowledge guide us. This would be the time, and evidently in this country, as we see by the current spike, that's not the case.
Yeah, and I think for me, what has been particularly depressing is that I would have actually thought that, one of the features of science that I think is very hard for the public, people who are not working in science, to understand is the provisional nature of the discoveries that we make. So anything we figure out is best to date for today. And when we have better instruments, we have more data, we have a deeper understanding, faster computers, our best understanding evolves and it changes. It very rarely fundamentally shifts, right? It's happened a few times. There have been a few revolutions, but that's really not how science progresses, but it is provisional. And I thought that the COVID understanding in this, during the pandemic, as our understanding was evolving and we were learning more, we were figuring out how to cope. And I thought that, this would shift everything because people would really have a ringside seat to see how science works. And I said, as you pointed out, I think unfortunately everything is so politicized that, there just isn't room for people to think clearly and understand what's going on their own. We're a little too easily fed by information from other sources without the critical capacity to be skeptical, to ask questions and judge it.
I think it's ironic because, part of science is being wrong and finding your way out of being wrong towards a better, more complete understanding. As you say, everything is provisional. Yeah. But there's a notion in politics that if ever once wrong, always wrong. Like the truth should be ever completely clear, and it's considered very suspicious for one person to hold a certain opinion, and later change their opinion about things, which is in fact a very scientific thing to do.
That's right.
New facts come in, new understanding come in. This is the scientific thing to do. So people can look backward and point to places where, okay, the scientific understanding used to be a little different. Therefore, no point in thinking about this anymore. Better to go for the sureties and assurances as we get from our favorite politician. This is depressing to me. That kind of certainty should be a source of some suspicion. And
I really hope, and I hope, people like us who are continuing to be excited about science and the work that we do, that, young people are not deterred from joining this profession. It's a wonderful life. It's a very fun career. And I don't know about you, but a lot of the times I feel so lucky to be paid for doing what I really enjoy doing, that I'm obsessed and excited about. And it doesn't feel like work. The actual, it's just so much fun. I really hope that, that's my concern, is that, this should not deter younger people from not just believing in science, but wanting to participate in research in science and technology, because the opportunities are tremendous across fields. I mean, the field of Bose-Einstein condensates, superconductivity, low temperature physics. There's a real sort of revolution, right, in these fields now. It definitely in astrophysics and cosmology, there's a revolution afoot. I mean, the revolution really is we have this moment of grand convergence where our theoretical understanding, the capacity of our instruments and make measurements, and the sophistication of computers are all kind of meshing and matching really well. And that's why you see all these discoveries. Like, every day there's a press release, you found another black hole, they found a new stellar nursery, or the most distant galaxy, the record keeps shifting. I mean, same is true in your field too, right? In experimental physics, there are all kinds of amazing things that are happening, and many opportunities for young people.
That's very, very true. And one thing I'd like to emphasize is that there is this stereotype of the scientist being the sort of lone eagle, very antisocial, working in his or her lab nonstop. And I don't know if it was ever true, but it could not be further from the truth today. Scientists are an extraordinarily gregarious animal. There's everything is done with other people, and that's a lot of the fun. I mean, these days when I go to conferences, it's partly to learn new physics, but it's partly to see my pals from around the world. And it's one of the things which made it such a gratifying career for me, is all the people I've met and known from 100 different countries, 50 different countries, people who I never would have met otherwise. That's just, I find so exciting and gratifying.
Yeah, and I think that, physics has always been very international and very global. And I have to confess that, like you, for me, travel and meeting people and interacting and figuring out how different people think about the same kinds of problems that we're working on, I think that has been a really sort of seductive part of this career. And so the pandemic has been particularly bad because we're not able to go off for our workshops. And I think we physicists are very lucky, right? We have some of the best conference centers and sites in the world, beautiful places to go and hang out. So miss that terribly now. But I mean, just to wrap up, because I think it's time for the Q&A, I was kind of curious, Eric, if you had anything you wanted to say to a lot of the early career researchers. We have a lot of graduate students and postdocs who are already in science, for whom this pandemic has been particularly disorienting and dispiriting. So I was wondering if you wanted to say some encouraging words to them before we move to the Q&A.
I guess what I'd like to say is that seen as a fraction of your entire life, a year, even 2 years, it's not that large of time, and it applies to everybody. So it's not as if, the temptation is to think is like, oh, a day, I've lost a year of my life. Well, yeah, you've had a different year of your life. Many of the graduate students who've come to work with me come from countries where you have to do, for instance, a year of national service or something like that. So they were, digging holes in the mud, or whatever, they were privates in something like this for a year. And they didn't see it so much as like, oh, I've lost a year of my life. It's just something they sort of went to. We can sort of think of this as our year of COVID service that we all go through, and I hope it's not 2 years. And from there think, yeah, this has been strange, maybe unpleasant, but new in its way. And
I mean, just hang in there. Just hang in there. I think
they will, I don't want to say something fatuous like everything will go back to normal. Everything will go back to different.
Yes.
But it will definitely be better than it is now.
No, I thank you very much for that. It's particularly poignant coming from you after the kinds of sort of personal loss that you had to deal with. So you've had moments when you were put out of action from science for a while after the amputation. So thanks very much. So let's move on to the questions. And I think we have a couple. So we have Erica Nolan, who asks, how did winning the prize change you, both personally and as a scientist?
I would say that winning the prize that happened in 2001, it was 1995, 6 years earlier, that the discovery happened. And that changed my life enormously. I went from being an obscure assistant professor to keynote address. In terms of sort of my relationship with the people that I care about so much, my fellow physicists, the change actually happened 6 years earlier. The Nobel Prize itself, fractionally speaking, was a smaller change. It was nice. It meant like I got to do some travel. I went all around the world on a sort of a scientific goodwill tour, which was really exciting. Still do some of that. But, you know, I live in a college town in the United States where scientists are not particularly held in huge regard. I would say that on any given day, walking down the streets of Boulder, there are 3 or 4 college football players that people will recognize more easily than you would recognize me. So it's not that I've gone into this new level of extraordinary celebrity or anything like that. It became a little easier to get my grant proposals accepted, but they still get rejected, which I find very frustrating. I want to say, do you know who you're dealing with here?
Let me just say, some of us are, you know, struggling with our grant proposals as well, you know, and without the aid of a Nobel to bolster our reputations. Yeah, but so we have another question from Lauren Fernandez, who asks, how would you describe your approach to physics? Are you both motivated by the theory, or do you take a more practical approach? Why don't you take a shot at it first, Eric?
Well, I'm an experimenter, which means at the end of the day, I have to be practical. I keep up with a theory in some cases, but not all of it. I sometimes will go to a series of theoretical talks and realize how profoundly I'm over my head on occasion. But I'm sure, Priya, that you don't have that experience.
Not really. I mean, I think there are still sort of very sort of, you know, mathematical parts of theory that are difficult for me as well. So I am very interested in building theoretical models which you can confront with data. I like that sort of confrontation of data and theory and sort of refinements of the theory. I have never been, you know, when I was starting graduate school, I had the choice. I finished at a time where, you know, string theory was going through its sort of first wave. So we're going through a second wave now, but the first wave. And because I did maths and physics as undergraduate degrees, you know, I was poised to really be a string theorist. I could have done that, but I didn't want to do that because I really felt that, you know, you're not making contact with observational data. And so what really to me is the kind of work. So it's like, you know, what I do, I really think is kind of building storylines, but then you kind of, you know, the story has to conform to what you see in the universe. But very much driven by observations.
If I'm not mistaken, Priya, some of your work is really challenges the current understanding of dark matter, right? Like maybe the understanding that is overly simple.
Yeah, so I think, so we just had a result that came out last month, a couple of months ago, actually, in Science, where I think we have, you know, there have been a lot of questions about, you know, the nature of dark matter because, you know, it dominates the matter budget in the universe, but we haven't found this particle. Once again, you know, problem with the very early universe, we don't know what particle it is. And we had all been fixated on a particular kind of particle, kind of a sluggish particle that doesn't interact very much, very lazy, cold, dark matter. And there have been challenges. It's a very successful theory. It's actually a paradigm now that describes, you know, the formation of structure in the universe and galaxies and everything. But there have been questions about this theory, places where the data and the observations kind of clash a little bit. So there have been other places where they looked like there was a crack and they were all resolved because, you know, had to do with we didn't understand something well enough and so on. But we recently found a crack that I think is very intriguing. And what's intriguing about it is the two possible resolutions are both kind of transformative. One is either there's something missing in our current methods of simulation. which is big because, we cannot do controlled experiments in cosmology. Simulations are our experiments. So if there's something missing, it's profound. We rely on these simulations enormously. And of course, the other possibility is that we have the nature of dark matter potentially wrong. So you're right. So, confronting these two often, I think of myself as someone who's looking for these gaps, a gap between. So there are lots of questions piling up. So let me move to the next
Bring
one.
Bring them on.
So we have, could we ever get a telescope that could see the surface of a planet in another part of our galaxy? Thus looking at surface as it was thousands of years ago. I think it's a really good question.
This is definitely your question.
I say part of the challenge, a challenge with actually directly imaging any other planets. So as we all know, we found thousands and thousands of planets around other nearby stars. So multiple solar system like configurations. But the problem has been directly imaging the planet is very hard because the light of the star is really challenging. And it's often too bright to actually be able to directly image it. So, but we've been finding them indirectly, and the hope is that we should actually be able to do something quite different, which is not quite see the surface, but actually zero in on the composition by looking at spectra, so that every chemical element in the universe has a unique fingerprint. So we might be able to infer what's on the surface by looking at the spectrum. And that is very much within the realm of possibility with the upcoming James Webb Space Telescope, for example. Even the James Webb, which operates in the infrared, so it can detect radiation in sort of 1 to 30 micron range. And we expect a lot of signatures of elements in that range. And so we should be able to say something about the surface and the composition, hopefully. The next question is...
Imagine if... Go ahead.
No, sorry. Go ahead. No, go ahead, Derek.
No.
Okay.
Next question.
Okay, the next question is, winning laurels, does that put pressure on your current work?
Not so much. If there's pressure, it's self-generated. I think there are some people who think, oh, I've won a Nobel Prize. I can't work on anything small again. Everything I do has to be at least at that level of significance. And which is usually a bad approach to doing physics. It's more like you were saying, is you look for little inconsistencies, a little thread to pull on. Maybe it leads to something big and maybe it doesn't. But if you're sort of saying, I won't even think about it unless it's a earth-shattering problem, you'll miss a lot of exciting things and probably won't find the earth-shattering problem either. So I don't work on, go ahead.
I was curious that, did it make you want to find another problem that you could crack? Did you want to go deeper? I mean, did it change your mindset in terms of what kinds of problems you thought were interesting?
Not so very much. I mean, I still work in Bose-Einstein condensation. I have an ongoing research program in there. I've been doing that now for, 20 years, 25 years. And many of the things I work on in ultra cold atoms, as it's called, Bose-Einstein condensation, you would call them small problems. They're problems of interest to the specialists. They're not going to set the world on its ear. But that's okay. They're exciting. To me, they're interesting, and who knows what directions they can lead in. So I still do that. But it is the case that I had the freedom to start this project to look for this asymmetry of the electron leading to a better understanding of this profound imperfection at the beginning of the universe. And that was obviously a big idea, right? A big project required a long horizon, and it's definitely swinging for the fences, to use a baseball and possibly a cricket metaphor, I'm not sure. And so, yeah.
Yeah, so I guess it sounds like, and I think, in many ways, like getting tenure similarly freed me to working on problems that had a longer kind of, you can take a risk and work on a problem that takes many years to sort of actually uncover and do. And so I can imagine that it's freeing in some way in terms of choosing what you can do. So I have a question, a final, I guess, a question from an old fan of mine who saw me last year at Houston, and she says, what about black holes? Are they hiding imperfect portals to other parts of the universe? Oh, that's a very interesting way to phrase what black holes might be. So I think this is a good place to wrap up as we are out of time. Thank you so much, Eric. This was a lovely conversation, and look forward to seeing you in Boulder, hopefully next year.
See you after COVID.
That's right.
This has been a pleasure.
Thank you. Thanks to JLF for organizing this and allowing us to have this sort of smooth flowing conversation in these very odd kind of circumstances. It's so weird when you can't really look at the other person in the eye and speak. Well, I'm sort of looking at Eric through Zoom, but in reality. Thanks so much for making it feel sort of warm and a friendly conversation, setting the atmosphere for it.
Thank you, Eric, Cornell, and Priyamvada Natarajan for that fascinatingly and truly warm conversation. Thank you all for watching and being a great audience. We encourage you to buy the books of our speakers that are available through the Boulder Bookstore for the US and from Full Circle for India. We hope that you all enjoyed all these conversations and sessions that we've been presenting, and we'll log back on tomorrow for another set of amazing sessions. These will begin at 6:15 p.m. Mountain Standard Time, which will be 8:15 p.m. Eastern Standard Time. That's 5:15 p.m. Pacific Standard Time. And in India, it's going to begin at 6:45 a.m. Thank you. I'd like to take this occasion to thank all our partners. Thank you and see you tomorrow.
Thanks everyone for
I would call the Jaipur Literature Festival a living library, or perhaps even a library of life. Do join us as we share the excitement of ideas and of debate and dialogue, of the adventures of science, of the joys of poetry and music, the consolations of philosophy, the sense of literature and of life.
So much about the festival in India, the scale of it, the energy of it, and I just love the fact that there is this effort to bring it to other cities in the world.
It's a variety of topics. It's meaningful. I'm just excited. I'm feeling like I've learned a lot to think about, and I appreciate JLF coming here.
Going forward, it would be a very good thing to do for the community to have this event on an annual basis.
I think that when you hear so many different voices and perspectives about the South Asian diaspora and many other issues, you learn that there's a lot of history that you're not taught every day, and I think that that's important to bring in today's world.
I was actually really surprised by the camaraderie I experienced here and the way that people at JLF, both attendees and other panelists, seem to really connect profoundly to literature and care about it.
In 2020, our live version of JLF has been laid to waste because of COVID-19. However, nothing's going to stop us from coming in the way of bringing our writers and speakers to you in Boulder, Colorado, Houston, New York, and Toronto, Canada.
Teamwork Arts, bringing India to the world and the world to India through Indian art and culture for over 30 years. One of Teamwork Arts' signature events, the Z Jaipur Literature Festival, is the world's largest free festival of its kind. With daily interactive sessions, lively debate and dialogue, and international music performances every night, it's no wonder the festival attracts over 500,000 visitors a year. The Jaipur Bookmark, an international B2B event for the publishing industry, happens during the Z Jaipur Literature Festival and sees a confluence of publishers, writers, and literary agents. Teamwork Arts, producers of the Z Jaipur Literature Festival, have taken the flavor of the festival to international shores with vibrant events in the UK, Australia, and the US. Teamwork Arts takes India's artistic diversity to the world with almost 12 festivals of India across continents in a stunning array in over 40 cities. A feast for the senses, these are spectacles of dance, music, cinema, theatre, literature, and so much more. In each of these places, Teamwork Arts' colourful festivals of India are the high points of the annual cultural calendars. Be it Confluence in Australia, India by the Bay in Hong Kong, India by the Nile in Egypt, Ion India in Chicago, Shared History in South Africa, India in the Sunshine City in Zimbabwe, Edinburgh Fringe Festival, Kala Utsavam in Singapore, Sarang in South Korea, festivals in Abu Dhabi, Shanghai, Sweden. The list is dizzying. The Jazz India Circuit is an endeavor by Teamwork Arts to spread the word and sound of jazz across the country. The 2017-18 season, 4 festivals across 3 cities featuring over 25 stellar artists from India and around the world, including Jojo Mayer and Nerve, drummer-singer Jameson Ross, and Dave Weckel, who collaborated with the talented Mohini Day. The Mahindra Kabira Festival celebrates the spirit, lyric and verse of the 15th century mystic poet Kabir in his birthplace, the historic city of Varanasi. Kabir's poetry is about inclusiveness. Mahindra Kabira brings to music lovers an unforgettable experience of listening to leading exponents of the classical Banaras Gharana and rich folk traditions of music on the legendary banks of the mighty river Ganges, along with sessions on art and literature, specially curated walks with famous local residents and delectable local cuisine. Sacred celebrates the spiritual through music and its ability to heal. International artists collaborate with world music exponents from India amongst the most incredible desert settings on the banks of the Pushkar Lake. Heritage walks, meditation, talks and workshops are part of this weekend experience. Teamwork Arts so promotes and recognizes the best of Indian theatre through the Mahindra Excellence in Theatre Awards. The Meta Week in Delhi is an enthralling showcase of the 10 best nominated plays shortlisted from numerous entries received from across the country and across languages. The Meta Lifetime Achievement Award has been presented to leading lights of India's theatre industry. For the young and the young at heart, the Ishara International Puppet Theatre Festival brings local and international performances to audiences across several Indian cities. while the multi-city Kahani Festival features interactive storytelling sessions and workshops championing the power of imagination. Bollywood Love Story, a musical. Our international touring productions such as Bollywood Extravaganza and Flamenco India have sold out shows across Europe, Egypt, Russia and Spain. Expressions International Contemporary Dance Festival showcases Indian and international productions, bringing together several dance genres for Indian audiences. Teamwork Arts, celebrating the arts. For more information, visit www.teamworkarts.com.
I think everywhere I've ever lived, I always looked for the library. They come to the library because they want to be with people.
Corporations are not people in the library. People are people, right? And so being able to come in and participate and learn and control that learning experience is what we offer to the community. And that's a beautiful thing. It can develop into something amazing.
We want them to recognize that they have the agency and the potential to create change and have a voice.
To become what they hope to be, to empower them to realize their aspirations.
No matter who they are, no matter what age they are, no matter what their background or ability is.
We're going to learn together, right?
And you know what? Not just me, because I want to create together, but I think we want to create together.
Give us your knowledge, give us what you do best. Give us your culture, give us good feedback, give us bad feedback, give us any feedback. Let us grow with you. Just come and ask too.
Ask a librarian. We're all here waiting to help you.
To work together, to collaborate, and to come up with a larger, louder voice as a collective.
We are bolder together.
We are wait.
Somos bolder juntos.
We are bolder.
Bolder?
Bolder together.
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 We're bolder together, we're bolder together.
Hello everyone and welcome to Kahani Online, where you discover the magic of storytelling in all its forms.
Very special guest with a very special story.
Please welcome actor and author Soha Ali Khan.
The story that I've chosen is called Someday. Here it is. And it's by Alison McGee and Peter H. Reynolds. It's a story that I've read many times to Inaya.
Everyone, grab a pencil, eraser and a notebook, as we are about to learn how to write short stories.
That's very simple. All you have to remember is 5 points.
Grumpy, we have a special story for you that dates back to the year 1962. Major Shaitan Singh Bhatti and his soldiers.
चीन ने भारत पर हमला बोला था. ये लड़ाई पूरा 1 महीना चली थी.
Our storyteller today is Katrina Zaev, all the way from Lithuania in
Europe.
Yes, in Europe. And she's going to tell us about some strange and fascinating mythological creatures.
Today I will introduce you all to Lithuanian mythology. I will show you our modern world full of hidden mythical creatures.
I will narrate to you an episode from one of our oldest epics, the Ramayana.
We'll be waiting to hear from you. Until next time, bye-bye.